To continue with Chapter 10, let's talk now about extratropical cyclones. These are cyclonic storms, low-pressure systems that form over the mid-latitudes. And in this table, Table 10.2, you see some of the distinguishing characteristics of a mature extratropical cyclone. So the size of them, they range from 1,000 to 2,000 miles, maximum winds anywhere from 35 to 45 miles per hour. They occur in all seasons, especially in winter in the northern hemisphere, and they happen pretty consistently. There's approximately 3 per day, poleward of 30 degrees north. So it's not just one that we're dealing with. We have a big country, so we can be dealing with several of these cyclones. They live for about 3 to 4 days. The energy source is the dynamic forcing. So there's that difference between warm air and cold air that's forcing the thing to live. The region of origins, these are mid-latitudes, and they are really driven by the polar front, as we talked about in Chapter 9. They tend to move from the east, towards the east, or towards the northeast, and their lateral speed is between 20 and 40 miles per hour. So these extratropical cyclones, or just low-pressure systems, or lows, are major weather makers for us here in the United States and everybody in mid-latitudes. So let's take a look here at the life of a mid-latitude cyclone. So cyclogenesis just means the birth of a cyclone. And we've identified 4 distinct phases here. The first one being the incipient cyclone phase, where we have our upper air winds, you can see by the dashed lines here, cold air in the north, warm air in the south, and 2 air masses that are meeting. So we end up with a low pressure, and remember around that low pressure system the winds are moving counterclockwise and in. And so at the incipient cyclone phase is just where we have these 2 air masses that meet. And we talked already what happens with a warm front and with a cold front, so now we're considering both of those things together. As the storm matures, it forms into what we call a wave cyclone. So you can see the isobars have deepened, so the polar front has deepened, and we end up with the comma shape. So if you look at the clouds here, they make a comma-shaped cloud, very easy to distinguish from a satellite image. So we still have our cold front and our warm front. Things have just intensified now. In the third phase, we have the beginning of occlusion. And occlusion, again, is where the cold air catches up with the warm air. So the winds are flowing in a counterclockwise motion, and the cold air is moving faster than the warm air. So it begins to catch up, and you see from the symbology here the occluded front symbol, which looks like a warm front and a cold front, but with both symbols on the same side, similar to a stationary front, but with both symbols on the same side because the thing is moving in one direction. So we have a deepening of clouds. We're going to see lots of weather, which we'll talk about here in a moment. The fourth stage is when we have bent back occlusion. So more mixing of the warm air and the cold air, and you see this occluded portion of the front has kind of bent back, and it's really wrapping around that low pressure cell, and that represents the end of the storm as the cold and warm air mix. Here's a satellite image of a typical mid-latitude cyclone in the United States, recognizable by its comma-shaped cloud. So you could see the cold front would be here, the warm front would be here, and the low pressure system is right in this area here. Let's take a closer look at what's going on weather-wise in different portions of this mid-latitude cyclone. So we'll break it down into the 4 directions: northwest, southwest, southeast, and northeast, beginning with the northwest, which is this portion of the storm here. So this is our cold air. You see these lines, or the arrows rather, representing the airflow around the low pressure, which is again counterclockwise and in. So we have cold air advection, all this cold air blowing into the northwest sector of the storm. We're likely to see stratiform type clouds, so layer type clouds like stratus and the many different types of stratus clouds. and we may see some precipitation, but non-convective. There's no convection going on here. It's just the stratus, like nimbostratus type precipitation. If we look in the southwest portion of the storm, which is down in this area here, we have the cold front, which is to the south of the low pressure cell. And here we've got that cold air displacing the warm air. So we have rapid uplift of the warm air, and right in front of the cold front, you're going to see thunderstorms. So the symbols here, you can read what they mean across the bottom. We're going to see our thunderstorms right in front of that cold front. The squall line is just a line of thunderstorms that literally is just right in front of that whole cold front. So this is our cold front, and then behind the front we have cold air, and it's mostly sinking air, so clear skies, cooler temperatures, and rising pressures behind that cold front. And then in the southeast portion of the storm, which is down here, we have the warm air mass, so nice mild conditions. You can see there's no real precipitation in this area. It's all the warm air. If we look at what's happening in the northeast, this is where we have the front, the actual warm front. So we have some overrunning that can take place as that cold air catches up with the warm air closest to the center of the low. And we can see here maybe some fog, maybe some drizzle, maybe some rain. It would be stratus type rain again. And so you can see all the different sectors of what's going on. So as the storm is moving in your location, remember this whole thing is being driven by the polar front, the upper air winds. So the whole storm is making its way to the east at the same time that it's rotating. So it's a lot of factors in play here. There are a few different tracks that these cyclones follow. As a general rule, the cyclone center, so the low pressure center, is moving forward in the same direction, but about half the speed as the upper air winds. And the upper air winds are often called the 500 millibar winds, so the winds that blow at 500 millibars, where friction is not an issue, so the winds blow faster. So that low pressure system is moving right along with those upper air winds at about a half of the speed. It slows down. Why? Because of friction at the Earth's surface. So these storm tracks that we'll see a map of here in just a moment tend to converge toward the northeast. Everything's moving that way. Storm tracks appear to originate just east of the Rocky Mountains, but they actually form over the Pacific Ocean, way up by Alaska. And as that storm travels over the Rocky Mountains, it kind of loses its identity, but then it regroups once it crosses the mountains and makes it to the Great Plains. Typically, cyclones that form in the south have more moisture in them because they have access to that maritime tropical air. And cyclogenesis is more frequent in the winter, when we have the biggest difference between cold air and warm air, and that polar jet really drives weather for us in the United States. A special type of storm that you probably have heard of is called a nor'easter. These happen off of the eastern seaboard, off of the North Carolina coast, and they tend to track toward the northeast along the east coast. So there's two things going on with a nor'easter. There's the movement of the cyclone as it kind of makes its way across the United States land and crosses over into the Atlantic Ocean. So there's that movement. And then there's the counterclockwise flow of the winds around the storm center. So with a nor'easter, basically what happens is the storm has, it's leaving land and crossing into the ocean. So very different situation. And if the upper air is favorable, it can cause the storm to intensify. The mid-latitude cyclone intensifies once it goes offshore, and it becomes a nor'easter. It becomes a stronger storm, and the direction of the winds kind of push it back onto land instead of having it drift off into the ocean. Here's the map of principal cyclone tracks, and you can see they all have different names, and they all kind of converge in the northeast because that's the general flow of the polar jet. So they can start in different areas. It just depends on where those two air masses meet up and where that polar jet is dipping down. So in the winter, you're going to see them kind of form, depends. In the winter, we get the polar jet kind of dipping down low. So we might see them form over here and then follow a track like you see some of these dramatic ones. If the polar jet's really low, you can have the whole storm kind of ride down here in the south. And in the summer, they typically form and follow a track that's further to the north. So let's take a look here at two possible tracks of a cyclone, a mid-latitude cyclone, as it's approaching Chicago. So meteorologists are looking and they see there's a mid-latitude cyclone and they want to forecast the weather for Chicago. And so they've identified two possible storm tracks that this system can follow. So they're going to start talking about the weather for the next few days, and these storms take, like 2 to 3, 4 days to make it across. So it's within prediction range here. So if track A is the track that the storm follows, Chicago is going to be on the warm side as the warm and cold fronts pass. But if the storm follows track B, Chicago is going to be on the cold side. So it could be two very different forecasts depending on which track that storm follows. This is a table, I know it's kind of hard to see here, but you can look at it in the book, that would show the weather conditions for Chicago depending on if it's track A or track B. So track A is here on the left, track B is here on the right. You'll see specific winds as the system begins to develop and move along. You're going to see the winds shift in a particular way depending on if it's track A or track B. As the front passes, we're going to see for track A a warm front and then the cold front pass. But if we follow track B, we don't really get the front pass. We're just going to get a bunch of cold air that comes in. So with track A, you're going to see a lot of weather happen. You're going to get warm air advection and then suddenly cold air advection. So these are nasty storms. I grew up in the Midwest and we have these all the time. So it's really nice, beautiful weather for a day or two, and then bam, there's that cold front and everything kind of gets cold and nasty. And then the air pressure tendency. So falling, 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 and then rising, rising, rising. For track A, remember it's falling as the low pressure gets closer, and then once the low passes, the pressure begins to rise again. And same thing really for track B. Here's one of the tracks, the Colorado track, which is typical for a winter storm. And you can see the mid-latitude cyclone. So here's the low pressure that's defining the system. Here's high pressure behind it. And you see the different symbols here. So it's winter. Up here in the section where we have our warm air, we're going to maybe see some snow and some freezing rain if conditions are right. And then here where the cold front's coming in, we're going to see our snow showers and then maybe a squall line of thunderstorms right before that. So you can imagine what the weather would be. You'd get these thunderstorms and then suddenly snow right after that. And then by the warm front, remember this is the mild area, so no real weather here, but right in front of it we're likely to see rain. The temperature would not be cold enough for snow. So the places that are getting the snowy weather are going to be where all this cold air is dropping down from the northern latitudes and interacting with this low pressure, this mid-latitude cyclone, to either create snow or snow showers or maybe even freezing rain. On a weather map, when you see this dashed line here, this represents the squall line, so that line of thunderstorms right before that cold front. Okay, we'll pick up with these regional wind systems in the next portion of the lecture. Bye for now.